Welcome to Lecture 9. Today, we are examining the Cisco Adaptive Security Appliance, commonly known as the ASA. Historically, securing an enterprise network required a fragmented approach. Administrators maintained distinct hardware units for different tasks, leading to sprawling racks of equipment. Passing traffic through a standalone firewall, routing it into a separate VPN concentrator, and inspecting it with an independent intrusion prevention system created severe operational friction. Every extra box added latency, points of failure, and configuration complexity. The Cisco ASA resolves this fragmentation. It is an integrated security device designed to consolidate those disparate roles into a single platform. Within one chassis, the ASA delivers stateful packet inspection, provides IPsec and SSL VPN support, acts as an intrusion prevention system, and manages network address translation. To utilize this appliance, we must first deconstruct its internal traffic control logic, and then walk through the strict sequence of commands required to configure it. By merging these roles into a unified architecture, network defense moves away from stringing together separate physical barriers. The security perimeter becomes a software-defined logical rule engine, evaluating every packet in a single, centralized step. The ASA evaluates all traffic based on interface security levels, running on a strict numeric scale from 0 to 100. We begin with the inside corporate LAN zone. Containing sensitive data and trusted users, it is assigned the maximum trust level of 100. Opposite is the outside zone, representing the public internet. It is completely untrusted, receiving the minimum trust assignment of 0. Finally, the demilitarized zone, or DMZ, holds public-facing systems like web servers. It is semi-trusted, typically assigned a level 50. These values dictate the first default traffic flow rule. Communication originating from a higher security level and moving to a lower one is permitted by default. If an inside user at level 100 requests an internet web page at level 0, the ASA allows it. The reverse applies for the second rule. Communication originating from a lower security level attempting to reach a higher one is categorically denied. If an unidentified user on the level 0 internet attempts to probe the level 100 LAN, the connection is instantly repelled. This default denial is absolute, unless an administrator configures a specific access control list to explicitly permit that exact traffic. Assigning a strict numeric value to each interface creates a mathematical baseline. Before a single custom rule is written, the appliance knows exactly which traffic to drop, eliminating the risk of contradictory configurations. Translating that logic into a functioning network requires a rigid, 5-step configuration sequence. Step 1 initializes the physical interfaces with an IP address, name, and security level. In the CLI, we configure the outside interface. Name if outside, security level 0, IP address 203.0.113.1. We repeat this for the inside interface. Name if inside, security level 100, IP address 192.168.1.1. Step 2 requires network address translation, or NAT. Internal networks use private IP addresses that cannot be routed publicly. Before traffic leaves the outside interface, NAT translates the private internal IP, like 192.168.1.10, into a publicly routable IP address, such as 203.0.113.10. Step 3 is the creation of access control lists. An ACL is a highly specific filter that dictates exactly which protocols and IP addresses are allowed or denied through the firewall.
Because the ASA inherently denies all traffic moving from a low security level to a high one, ACLs are the only mechanism to punch precise, intentional holes through that defense. For example, to allow external users to view a company website, we write an ACL that explicitly permits inbound HTTP traffic targeting the specific IP address of the web server residing in the DMZ. Step 4 is binding. Writing an ACL does nothing on its own. The rule remains inert until it is actively bound to a specific interface and assigned a direction, applying the filter to incoming or outgoing packets. Step 5 concludes the pipeline by enabling routing. The ASA requires a default route to direct outbound traffic toward its final destination. If a packet is bound for an external network not directly connected to the ASA, the default route instructs the appliance to forward that traffic out to the next hop gateway on the Internet. Interfaces, translation, access lists, binding, and routing. Skipping or reordering any of these 5 steps breaks the packet flow logic and leaves the network either vulnerable or completely isolated. Applied in production, the ASA typically supports 3 primary architectural configurations. The first is the enterprise firewall deployment. As internal users access the web, the ASA's stateful inspection engine logs the outbound request and independently verifies returning data against that active session. This stateful tracking dynamically allows legitimate return traffic through the perimeter without requiring the administrator to write permanent inbound access rules. The second configuration is the DMZ implementation. Public-facing web and email servers are placed in their own level 50 network segment. This isolates risk. If attackers compromise a public web server, they are trapped in the level 50 zone. Any attempt to pivot into the level 100 internal corporate network is blocked by the ASA's default denial rules. The third application is VPN integration. An encrypted tunnel stretches across the unsecure internet, connecting a remote employee's laptop directly to the perimeter. The ASA terminates the encrypted session at the edge, authenticates the user, and securely drops their traffic onto the high-trust internal network as if they were sitting in the building. A single ASA chassis executes stateful inspection, isolates the DMZ, and terminates remote access tunnels simultaneously, providing structural security across vastly different network topologies. To summarize, the ASA controls traffic flow through strict security levels, utilizing NAT for routing, ACLs for precision filtering, and VPNs for secure access. Managing this appliance requires strict adherence to the principle of least privilege. Administrators must grant the absolute minimum network access necessary for users and systems to perform their designated tasks. Broad rules covering entire subnets invite exploitation. Because the ASA processes all connections, continuous monitoring of system logs is required to detect anomalous traffic spikes or repeated access denials. For complete defense in depth, the ASA's firewall capabilities should be paired with dedicated intrusion detection and prevention systems, combining structural access control with deep packet behavioral analysis. To the computing students here at University Utara, Malaysia, mastering this architecture is a core requirement for enterprise network engineering. Plugging in a metal box does not secure a network. Protection is built through the rigorous, logical configuration of the trust boundaries within that hardware.